Back, everybody. We're just going to finish up this example that we're right in the middle of for posterior prediction. We're just finishing up an integration. We are doing this integration right here. And we chiseled away at this for a long time, and we got right here. So I'll just point out what we did is we expanded this thing, minus 1/2 x tilde minus mu squared over sigma squared. That's the sampling density. And then I took the posterior distribution we were working with on mu. I assumed a flat prior, so that is a normal distribution centered at x bar with variance sigma squared over n. So that's just this. E to the minus 1/2 mu minus x bar squared over sigma squared over n. So, and then we just started working at this integral right here. So what we did first is we expanded everything, brought everything into a common exponent, and then we factorized out that. So keep in mind our distribution is defined in terms of x tilde, so we can't throw it away. It doesn't have anything to do with what we're integrating over, so we simplified life a little bit. We chucked some x bar stuff when we expanded that thing out, and that thing got squared right there. We just threw that away. So, because it just factorizes out. And at the end of the day, this is what we got. This was the inverse normalizing constant for the normal distribution. So if you're integrating over mu and you've got the quadratic term in terms of mu, you can recognize where the variance is. So for that integration that you're doing. So that was just right here, and it was this thing. So this was the data variance, and this is the variance for mu. So where both of those things came in. So remember the original conversation, we're accounting for uncertainty in the future, and we're accounting for uncertainty in our estimate of mu that we're integrating out. So when that shows up here, when we invert everything we got back here, then we look for the -2 linear term in this in terms of mu, and we recognize this thing right out in front of it. We multiply that by the variance, what we got right here, and it gives us our expectation. And so the only part that was missing from this to make it an actual normal distribution was the normalizing constant, which is this thing, and I should probably be a little bit more clear. This was right here, square root of 2 pi times b star. So if you wanted this integral to be exact, right here it was this, and we got rid of this because v is just defined in terms of sigma squared, which is known for our example. For your example that you're going to be doing in the homework, you don't know sigma squared, so if you throw away that variance term, you will have made a mistake. So be on the outlook for that. So we just have this expectation and that variance, and it turns out the normalizing constant is always this thing times e to the plus 1/2 e squared divided by v. So that's something you can either remember, or you can do what I did on the board, and I just expanded what a normal distribution looks like to see which term was missing from everything. It's the same as completing the square, but it just omits a step. You're expanding the square. So we have this right here, and now we need to recognize this whole thing that we wrote down. So this is some normal. How can we tell? Good indication right there. E to the minus x tilde squared. We probably need to look at this part as well. We notice there's an x tilde in that as well as getting squared. So we can already recognize that this is a normal distribution. So the only thing we need to do is recognize what the mean and the variance is. So we're going to apply both those steps again, expand all of this, recognize its quadratic term now in terms of x tilde, and its -2 linear term in terms of x tilde. So let's just do that. Rewrite this out again, e to the minus 1/2. Actually, let me do a little bit of simplification just right here. I think we left it like this last time, but I can get rid of those sigma squareds. And I can tuck this n plus 1 into everything. So this is going to be x tilde over n plus 1 plus x bar over n plus 1 divided by n. So I'll just do that and simplify a little bit. We're going to have a bunch of sigma squareds in here that are going to cancel anyway. We can cancel now, or we can cancel later. So this is going to look like x tilde squared over sigma squared, still the same part, and now I'm just going to plug everything in. I always think that should be a negative sign, so I'm going to reinforce to myself that's actually positive. So you have to keep track of what happened to this normalizing constant in this integral, but it is positive. So now let's just plug everything in. So this is x tilde over n plus 1 plus x bar over n plus 1 divided by n. And this is all squared. And then I'm going to divide it by this variance right here. So divide by that variance right here, or I can multiply by the inverse of that thing. So this is n plus 1 over sigma squared. So I'll just multiply by the inverse of it. So now we have some more cancellation that's going to go on here. Let's just do some expanding. So this is e to the minus 1/2 x tilde squared over sigma squared. And now we're going to expand everything. I'll just keep this separate for now. E to the plus, oh, and there was a half in here. Just forgot it. 1/2. This is going to be x tilde squared over n plus 1 squared plus x tilde, 2 of these, times x bar over n plus 1 times n plus 1, that one divided by n. So plus x bar squared over n plus 1 over n. This is squared right here. And now I'm going to multiply this by n plus 1 over sigma squared. So there's some cancellation in this. I can first get rid of that. That's just a constant in all of this. We've been throwing away and factorizing out all of the constants. So we'll do it one last time. Get rid of that. We can write this up to proportionality. So now I'm going to probably do a little bit of cancellation. Let's get rid of those n plus 1s. I'll get rid of that. I'll get rid of that right here. And then I might tuck this sigma squared right in here. So we can bring that in and slide it right in again. Let's just rewrite this. This is e to the minus 1/2. And I'll just combine my quadratic terms. So I have an x tilde squared, 1 over sigma squared. I've got one of those. And now I have this one as well, right here. Don't forget about that sigma squared right here that needs to be brought in. And so what does this look like? This is going to be plus, let me try to make a mistake and see if you can catch it. So plus this thing right here, 1 over n plus 1 over sigma squared. Is that right? Minus. Boom. Where the minus sign comes from, I'm tucking it into that minus sign right here. This one has a plus. So if I'm going to flip the sign on this whole part, I need to throw that minus sign right there. So that's that. Minus, again, I need to change the sign right there. 2 times x tilde, x bar, over n plus 1 divided by n times sigma squared. So that's all my stuff right there. So this would worry me if I were staring at that right there. I know variances have to be positive. I see a negative sign, so I'm immediately freaking out. You know, did I make a mistake? It turns out this is correct, but that's something you would want to pick up on. If you return this and it did happen to be negative, I would think there's a major problem right there. So this is correct. So now we can recognize everything. So we're after this distribution, x tilde, given x, and sigma squared. We know this is some normal distribution, and it has some expectation. I'll put a tilde over the top just to match the notation there. So, and some variance. And now we're able to recognize what those things are. Just give myself a little bit of room here. is variance. I'll go for the easy one first. So 1 over sigma squared minus 1 over n plus 1 sigma squared inverted. So now I'll just make everything a little bit easier. This is n plus 1 here. I'll give it a common denominator, n plus 1 upstairs. So this is equal to n plus 1 minus 1 common denominator, so I can combine those two things. This is n over n plus 1 times sigma squared. 1 over sigma squared. Inverted. So this is equal to sigma squared. It's n plus 1 divided by n, which is equal to sigma squared times 1 plus 1 over n. So we've now freed ourselves up from our intuitions. We don't have to think about that anymore. This is math. And so, but I think that this answer does make sense. It has all the intuitive properties we already discussed. It matches what we guessed. But if you want to be sure, you go through all the details and you work out the math. So this is our variance. So this is just sigma squared plus sigma squared over n, if you like to write it that way. So this is the variance of our predicted observation, and this is the variance attributed to estimating mu. Keep in mind, in a prediction problem, you can never get rid of the inherent variance of the problem. So that's built into the process. So if people are ever asking you to predict something and to be sure, you should tell them it's impossible. The only part of everything we can drive down is our estimation and the parameters. So that's what helps us. So if anybody ever tells you they have a 99.99999% predictive rate, they're lying. They've made a mistake. So you always have some level of uncertainty in the problem. And if you don't see that level of uncertainty in the problem, somebody's fooling you. So important to remember. So we can just chisel away now, work through the expectation. So x tilde, I'll use the same notation we did before. Expectation tilde is just equal to this stuff right here times that. Or if you prefer, maybe like that. So you'll notice that term is sitting right here. So when I multiply all of this by that thing, all you're left with at the end of the day is x bar. Let's just write it down. X bar over n plus 1 over n times sigma squared times n plus 1 over n times sigma squared is equal to x bar. And that's what we guessed early on as well. So where else would this thing be centered? So in prediction, a lot of times you're going to use basically your data-driven inferences to basically center everything, at least in this example, this is how it works out. And all we're changing is the variability. Now that won't always be true for every single problem, so that everything isn't exactly where the original posterior on the parameters are centered. It just so happens that everything is normal here and there's a certain type of symmetry that we see coming through the problem. I'm sure everybody worked through that over the weekend and had already seen all of this. Hopefully you can repeat that in the future. So we'll keep coming back around to this, and hopefully we can recycle this part when problems get hard and we don't have to rewrite that every single time. So try to commit that to memory. Any questions, or would you like to see the easy way to do this without having to do all of the integrations? I will point out that setting up the integral and recognizing the form of what that integral is going to be at the end of the day, i.e. it's going to be normal, is the part you need to kind of imagine working through that calculation to understand what its distributional form is. But in terms of plucking off the expectation and the variance, that's rather straightforward in this example. So if you have a distribution that's defined by the expectation and the variance, you can take a shortcut. So is everybody familiar with this? This is just a little bit of review. So if I want to find the expectation of some random variable, I'll just say it's z. I can do it like this. Expectation of z given w. Where w is just some other random variable. It can be anything. This is always true. Does everybody know this? Who does not know it? Awesome. So how do you derive that? If I asked you guys to prove it real quick, you guys would be in great shape, right?
By discrete random and infinite.
Do what?
You mean prove this one?
Yeah, how would you prove it?
This by discrete random and infinite.
Okay, if I said it was continuous, would it be any harder?
No.
Probably not. Integral and summation signs, it's all linear operators. They interchange exactly the same. So it doesn't really matter if we're adding up in continuous space or discrete space. So somebody just indicate the key word I need to know that you know how to do the step. Okay, we might have a quiz on Wednesday then. So I would check this. You guys told me you all know it. You've seen it before, you're familiar with it, you use it all the time. That's what I heard, or at least I'm pretending to have heard that. So let's see. We might recap that and do a derivation. But the easiest way to do this is just set up what the left-hand side is, integral z pz dz, where this is its density. So I'll assume that it's continuous. So, and then I can just do something like this. This whole thing is the expectation of some other expectation. So I'll do them in 2 steps. You can just write this down. The expectation of z on w is the integral of z integrated with respect to z given w's distribution dz. So remember that expectations are always functions of what they're conditioned on. So it's not a function of z. Z is gone. You've integrated out that z right here. And so this outer expectation is just the integral of the integral z f z given w. So this is just this part, dz. And now I'm going to integrate this with respect to w. And this is w's marginal distribution. So you can prove that these 2 integrals are the same. The thing you need to do and justify is that you can interchange the order of these integrations. But I'll just point out, you can just flip those 2 things around and show that these are the same distributions. Drop w right through here, get its joint distribution, now marginalize out w, and you'll have the margin on z, which is exactly the same thing here. So I think we just kind of constructed the proof. Here's another form for you. So in that same vein, there's a iterative variance formula. So variance of z, some random variable, can be written like this. The expectation of the variance of z on w plus the variance of the expectation z on w. Pretty inconsistent with my braces. So that's true too. How would you prove this? Start untangling the right-hand side and show that it's the left-hand side. So these are relatively easy calculations. If somebody gives you a formula and say prove that it's true, you just verify it. So work out the right-hand side, show that it's equal to the left-hand side. So start with the definition of what variance is. Start working here. Generally, I always write everything out in terms of continuums because that covers sums as well. If I say I'm integrating with respect to these point masses or something like that and turn the problem into a discrete problem, I think it all generalizes. Okay, this is also true. This is an easy formula to remember because you might get confused. Is it the expectation of the variance or the variance of the expectation? It's both of them and you just add them together. So hard to forget. So let's apply these. Keep in mind, posterior predictive distribution is really just a hierarchical model. So there's a hierarchy on the parameters that we're estimating, and then there's that other hierarchy on the forecast itself. So let's figure out what this is. Expectation of x tilde given all of our data and sigma squared. I'll just point out in this formula right here, if I condition this on some random variable, could be anything, then I can condition this on that same random variable and condition this outer one on that same random variable as well. So if you condition on the left-hand side, you need to condition all of your operators on the right-hand side. So that's what conditioning is. It means that that thing is held constant. So this can be any random variable you want or anything you want. It just needs to be conditioned on. So what have we conditioned on here? We've conditioned on those two things in our problem. So we'll carry through the same thing. We want the expectation of x tilde. So I'll just use the iterated form of all of this, and I'll plug in x tilde. I need to condition on something. That was my W before. So that just seems rather arbitrary, and it turns out as long as that has a density that integrates up to 1, these formulas are true. So I'll just put in this W with a question mark right there. What should we use for W? This is going to be conditioned on x and sigma squared. I get to know those. Those are right here. And I better condition again on x and sigma squared. You might think that the notation is superfluous and you don't need to write it down. You'll just remember it. But you might not when you're carrying through the steps. You might forget what these integrals really represent. So that's the reason I like to be really pedantic with my notation and just write it all in. So this is going to look like the expectation. Which expectation is this one right here? This is just the sampling distribution. So the data doesn't actually help me if I know everything about the whole problem. So I wouldn't pick any old random variable. I wouldn't just shove a Poisson in there all of a sudden. So it doesn't relate to the problem. So the thing I'll condition on in here is the random variable that we're integrating out. And so if you actually untangle all of these integrals that we're writing down, you'll figure out these are exactly the integrals we've already just solved on the board. So all of the math is exactly the same, but we just have some mathematical notation that ease our calculations. So I'm going to write down x tilde in the presence of mu and sigma squared. If I know both of them, the data doesn't actually help. And so we can just get rid of it because I know everything about the process. So what's the expectation of x tilde given mu and sigma squared? First question is which distribution is that? And we already know that's the sampling distribution. So that's a normal distribution that's centered at mu with variance sigma squared. You might like that notation down here to tell you what they're integrating with respect to, but that's always in the argument as well. So the expectation of x tilde given knowledge of mu and sigma squared, that's going to be mu. So, and I still condition on x and sigma squared. Those are these. Or sorry, those are these. Right here. So we've taken care of the inner expectation, that's mu, because we know about the sampling distribution. So the inner expectation is about the sampling distribution, and then the outer expectation is about the parameters that we're estimating. So kind of like those two steps in the process that we laid out before. So this iterated form is telling us all about those two steps. So the reason I like this notation is it tells me, oh, this is the posterior mean that we're looking for, and I get knowledge of sigma squared. So I know what the posterior distribution on mu is, given sigma squared. It's normally distributed, it's centered at x bar, it has variance sigma squared over n. So I know the answer. It's x bar. And that's exactly what we got for this thing. No surprise. Let's do this with variance. I'm going to say we want the variance of this specific distribution. I'll be really pedantic about the notation I'm using. I'm going to remind myself I get to condition on knowledge of the data, and I get to know sigma squared. So this is the expectation of variance of x tilde given. I'll condition on something. I'm going to condition on mu again. That's our placeholder for w. It's always going to work out this way. The parameters you're integrating over, that's what you'll condition on in this first layer of the hierarchy. So x and sigma squared, I like to write it all in, plus the variance of the expectation of x tilde given mu cap x and sigma squared. I need to remind myself that every layer of this I get to condition here, so I didn't write that in. So let me just open up a little bit more room. Plus, and this is going to be conditioned on x and sigma squared. So again, just a reminder to myself, I get to know those things all the way through the problem. So this, expectation of the variance, I'll do the variance first. Same argument before. If I know mu and sigma squared, the data doesn't help us with anything, so I can just get rid of that. So what is the variance of x tilde given knowledge of all the model parameters? It's sigma squared. So the variance of the expectation, this expectation is the same one that we dealt with over here. This will always happen. So this is going to be the expectation of x tilde given knowledge of the model parameters, and I can get rid of that as well. So this is going to be the variance of mu given x and sigma squared. So this is where I really like the notation that I've conditioned on sigma squared. If I solve this just sitting here, I think that's a posterior distribution that we're trying to figure out. But this is the expectation of sigma squared given the data, and I get to know sigma squared. So that's telling me sigma squared is just a constant. And so data doesn't help me with any of that, and I get to recognize that because I wrote it in right here. So what's the expected value of sigma squared given that I get to know what sigma squared is? Yeah, I hope so. So it's sigma squared. So this one right here is sigma squared, plus this one right here is a posterior distribution on mu. I get to know what that is. I get to know that. So we already know what this variance is right here. This is the posterior variance. That's sigma squared over n. So the variance of the predicted value given this information is sigma squared plus that. So I probably could have answered very quickly in the beginning when the question came up, how do I know to add these two variances? What I was thinking in the moment was, because I'm doing the iterated variance form in my head right now, and there's an add sign right in the middle, but it's because I did the calculation that I had the intuition. So I think it kind of really works that way. You need both, vantage points. Some reason to believe something, and then you actually need to always do that. Any questions about all that? So for any posterior predictive distribution, if you know what the posterior's expectation and variance are, and you're only after an expectation and a variance at the end of the day, and you know its distributional form, you can always apply these. So you might have learned these in a statistics class through hierarchical modeling, but just keep in mind all Bayesians are hierarchical modelers. So every Bayesian model is a hierarchy in the first place. So keep in mind that you can't apply these when you're using improper priors if I extended that to the hierarchy of the prior itself. But we're not actually doing inference on the prior here, so everything works out great. Okay, so make sure you're able to do this. I have it in the next homework that you'll be kind of working through all these calculations. There's a step where I say apply these formulas. You're just going to repeat what you've done here and just hopefully know I'm probably going to do this to you on a midterm and ask you about some other distribution, probably not normal. So it shouldn't be hard to pick which distribution it is. If you have trouble trying to predict which distribution I'm going to pick, any distribution we talk about in this class is fair game. So it might be exponential or something like that. Right now, I think we've at least talked about that through a gamma distribution. Might be Poisson when we get to that. So it could be binomial. So all of these forms apply to all of those problems. Okay, let's do something easier. I want to teach you just a couple definitions. So this is probably the easiest lecture in class. This should take me all of 2 minutes. I'll tell you real quickly what a map estimator is. So the map estimator is the maximum A-Posteriori estimator. So you can almost figure out exactly what this estimator is by the name. So you can tell a statistician named this. So very good. It actually even sounds cool, so they might have gotten help from somebody. So, but it's just maximizing the posterior distribution and figuring out where the argument is that maximizes that thing. So just an illustration of that. Say I've got some posterior distribution over some parameter, theta, and it looks like that. So there's two modes in here. This point right here is the maximum of the posterior, where I'm maximizing over theta. And this right here is the argument that maximizes theta. So this thing right here is called theta hat map, and it is the maximum A-posteriori estimator. So that's all it is. So let me just ask a quick question. Would returning the map to somebody in this example make a lot of sense to you? Somebody said, hey, what do you think theta is? Here's the map. Probably. There's a lot going on with this distribution. So I think we can all see, if you just report back one number here, you're probably excluding a lot of cool discoveries over here. So just respawning back with a map is probably not a great answer here. Just think about a normal distribution. So map estimator is a good estimator? Maybe. Yeah, it's symmetric. So it's heavy-tailed, so maybe that doesn't matter for a map. What about expectations? Would reporting back an expectation on a normal distribution make more sense than a map? They're the same numbers, and the median is the same as well. So sometimes they're the same and sometimes they're different. You kind of just have to think about what the distribution is and think about if your estimator is characterizing that distribution well. So maximizing things in high-dimensional space can be difficult. So here's just a question for you. Say I've got a distribution. I'll say I've got two parameters. I'll call it theta 1 and theta 2. Given x, and let's say I want to arg maximize on theta 1 and theta 2. That's our parameter set. And let's say I get back something that I call theta hat 1, theta hat 2. So these are the map. This is the map estimator. I am assuming that they're unique or something like that. So they're going to be unique as long as there's no ridges or flat spots in the space. So here's my question. Can I just think about can I turn this into two one-dimensional optimizations? So question, if I take theta 1 given x, and I find that by integrating out theta 2, bless you, d theta 2, I'll do it over all of its space, right here, and I define this, the margin on theta 2, given x, integrate over theta 1, can we just arg maximize these? Arg max over theta 1, call this theta 1, and I'll call this theta 1 prime hat. Call this thing the arg maximum over theta 2. I'll call this theta 2 hat prime. So here's my real question right here. Are theta 1 hat equal to theta 1 hat prime, theta 2 hat equal to theta 2 hat prime? So basically, can I just simplify this high dimensional maximization problem into a couple marginal problems and report back the maps on those? No. So anybody that's ever studied optimization knows this might not be the case. When would it be the case? If they're independent. So there might be some joint structure involved in those things. So if they're independent, that's true. If they're dependent, we don't know. It could be true. It might not be true. The only reason I point this out is I see a lot of people do this in the literature, that they say, I like maps. You know, they're robust to outliers and all that stuff. I don't want to worry about means. And I'll simplify the problem, look at the marginal distribution, and report back the estimates on the margins. It's a lot easier to do that. But there's no guarantee that that even is meaningful. So I just want to point that thing out. So high dimensional optimizations are typically difficult to do. And sometimes they're worth actually carrying out. I'll just show you an example real quickly. I just coded this up. I should say I coded this up years and years ago. But I made this distribution right here, just to exemplify the point. You can think about this as theta 1 and that theta 2, or something like that. If I rotate this around, I can see that that peak is much higher than that peak. Just get rid of that. I'll bring it back up. Boom. Look at that in a second. There's my distribution. I can see that one of those things that are centered, if you look at this, this is centered at -10, -10. That's where that peak is. And this peak right here is centered at 0, 0. You can see what I've done with this distribution is I've stacked a lot of mass in that margin, in this direction, and I stacked a lot of mass in the other direction too. So when I marginalize over these things and I add up all of this mass, marginally that peak is going to go higher than the other one, but it's lower jointly. So that's what you can think about. Maybe if you're thinking about jumping on maps, you might want to check for this sort of behavior before you simplify the problem and then publish a result that might not be optimal in any sense. I did draw the marginal distributions. So they look like this right here. So I didn't label which one was which because they look exactly the same. It's all symmetric and everything. You can see that when I stack mass on 0, this point is 0, this is the -10s, that got a lot bigger. So averaging and then maximizing over something, just remember what it's doing is you're adding up all the uncertainty in a particular direction. Does anybody know how I made this distribution? Looks pretty cool. I added some normals. How many normals do you think I used? There's 3 of them. So there are 3. So there's one right there. There's one going in the other direction, and there's one bivariate normal there. So if you just want to see real quickly, here's my code for doing that. Everything, most of it's just plotting in here. So I just have some means that I've centered in some places and some variances. Did the same thing up here, so I have some mean and some variances. So I have variance that's big in one direction and tiny in the other direction. That's what's thinning it out in one of the directions. So, and then I'm plotting them just right on top of each other. Bam. So there's 3 distributions in here. Then what I do with those 3 different distributions is I put weights on them. So the 4 different normal distributions, these are just grids of values. And then I put some weights on them that add up to 1. So I'll just point out this is called an additive mixture model. So all I've done is plotted 3 normal distributions in bivariate space on top of each other, and then I normalized them. So that's an additive mixture model. We'll come back to that concept later in class, but just adding together these density functions and weighting them with weights that add up to 1 is called an additive mixture model, and they're extraordinarily useful. So we'll learn all about them in a couple weeks' time. Any questions about that? I told you that was easy. Let me show you another concept. So you might not be quite as familiar with this. We've talked around this for a while, but I want to compare the concept of confidence to credibility. So somebody please tell me in words, just real quickly, what is a confidence interval? Imagine you're in Stat 101 class, you're going for the extra credit bonus point.
As a previous say confidence interval is some interval that we have some level of confidence, which is related to how frequently it contains the parameter. We have some level of confidence that it contains the parameter.
Okay, we've got some level of confidence in it, so what does that mean? So yeah, exactly.
So it's 95%, then
So let's say it's a 95% confidence interval. What does that mean?
95% of the time it will contain the true parameter.
Right, so if I repeat the process over and over and over again, I think I've illustrated this before. So for one data set, you can construct an interval. So question is if we repeated the process an infinite number of times, at what rate do those intervals cover the truth? So I'm going to imagine some problem, maybe something like this. So example, maybe xi's are coming from a normal distribution, mean mu, variance sigma squared. We'll make our life easy, say that's known. We don't know what mu is. So what I can do with all of these data points that we're going to get is I know a good point estimator is x bar right here, and then I can construct some interval. This is your typical interval. So I'll just write down times sigma over root n. This is the standard error. So these are the control, whatever these quantile points are. How many standard errors do you need to go up to contain so much mass? That distribution right here. This is a typical 95% confidence interval. So what it means is if I go and I collect n data points and construct this interval, the question is did it cover the true mu? So is mu in the middle of those 2 points, or is it on the outside of that interval? And so if I repeated the experiment some arbitrarily large number of times, if this is a 95% interval, then I might expect that this interval, the way that I'm constructing it, using this process of computing x bar and writing down the standard error, every time I recompute everything by doing another experiment, I'm going to have a new x bar. That thing is jittering around. So the question is how many of these intervals that I construct actually contain the truth? So it's a statement about coverage, and it's an a priori statement. So I can use that in other fields as well. A priori, before I've seen any data, I can construct a process that should cover the truth at some rate. And so it's a statement about the process. So for any particular data set and any particular mu, we don't know if it covered or not. So if we knew what mu was, we wouldn't do the exercise in the first place. So it's a statement about the process. So if I am delivering across campus 95% confidence intervals to people, and let's say that they're actual confidence intervals like this one, not asymptotic ones, not meaning as n gets bigger and bigger, this ends up covering at the rate that I say it's covering at. So a lot of these asymptotic things, you say that, well, if n was infinity, it would cover right. If n was infinity, your interval would be a point. So we wouldn't even be doing statistics. So that's my answer to the asymptoticist is, if that were true, I can drop out right now. And I know all the answers. So this is an exact 95% interval. I don't think that there's those issues with this. But this is a statement about building intervals, left and right bounds, and seeing how often they cover. So the people that have asymptotic intervals, if they say they're 95%, I'll always ask, what are they in reality? For your problem, for your data set, sizes of that. And if they say they don't know, I usually stop listening. So if you didn't do a simulation study to check, and they're actually 72% interval, 72% confidence intervals, why are we calling it 95? So, and that happens a lot. So I'll just point out, X bar is the random thing to a classicist. So what they're really looking for is they're making a probability statement on X bar, and they're seeing if it's between two bounds. Usually we'll write this like this, 1.96 sigma over root n. And this is going to be mu minus 1.96 square root n. So this is a probability statement about X bar. It's what's random, and it's checking to see if it's between these two bounds. So you need to input what mu is into this equation and ask a hypothetical question about a hypothetical mu. So you probably learned this in hypothesis testing, where they'd say your null hypothesis is some value like mu naught. You construct this interval. And if you don't like the statement about coverage, you can reinterpret this and you could say, for which values would I be willing to not reject the null hypothesis? And so we'll study that later on when we get to hypothesis testing. What people will do is they'll re-engineer this bound, and they'll write it down like this. X bar, they'll redistribute all of this, and they'll put the mu in the middle of the equation. This will be X bar plus 1.96 times the standard error. And this will be X bar minus 1.96 times the standard error. So they'll redistribute everything and they'll write it like this. Just keep in mind, when you write it like this is random and that's random. This is not a probability statement about mu, it's a probability statement about the bounds. So that's how non-Bayesians think about things. Now, Bayesian wants to do something a little bit different. They want to construct an interval on mu itself. And it turns out, if you ended up doing the posterior analysis, constructing a 95% interval from the posterior distribution, we could call that a 95% interval as well, and we have a different interpretation for it. We'll come back next time and just secure our minds in realizing the Bayesian actually will give you this interval right here under the flat prior, but they're making a probability statement about mu. The nice thing in this example is the Bayesian and the non-Bayesian both agree on what the bounds are. And they're both making 95% statements, but they're making 95% statements about different things. I don't see any room for argument in this. I think it's great. So I can interpret this is a belief interval of where mu lives, a probability statement about mu, but I can also advocate for a property on that interval and say that interval has a coverage rate of 95% as well. So it turns out for this example, the Bayesian and the non-Bayesian have slightly different viewpoints. They end up giving me the same interval, and it turns out you can adopt both viewpoints. Turns out that's not always true. So that's what we'll come back next time and study. So I'll give you an example where the Bayesian and the non-Bayesian disagree with each other. So we'll recap this for 5 minutes next time, and then we'll jump into an example where the Bayesian and the non-Bayesian are talking about totally different things. Thanks, y'all. That's it for now. Keep in mind, we will do a review session on Thursday. We got fall break this Friday as well, and we'll also do another review session next Thursday. So 2 of them. Thanks.